In this session, we're going to talk about recurrent neural networks. These are what we're going to talk about today. First, we're going to have a look at one example called language models. This motivates why we need recurrent neural networks. And after the motivation, we're going to talk about what recurrent neural networks are. And these are sometimes mostly abbreviated as rnns. And after that, we're going to discuss some applications of rnns. And we're going to talk about some limitations of vanilla rnns and how we can resolve those limitations using gates. And finally, I'm going to summarize this session. Okay, first of all, the language models. What is language modeling? Language modeling is the task of predicting what word comes next. For example, given the sentence, the students opened their, and in this blank, many words can come. And language modeling is the task of predicting what words can come given context. So here, the students opened their is the context. And this is what we need to predict. And more formally, and so here, this blank can be books, laptops, exams, or minds. And formal definition of language modeling is like this. Given a sequence of words, x1, x2, and xt, language modeling targets to compute the probability distribution of the next word. So you can express this using this equation, conditional probability, and this is the condition or the context. And xt plus 1 can be any word in the vocabulary. And this vocabulary contains around 50,000 words generally. And a system that does this is called a language model. Okay? And you can also think of a language model as a system that assigns a probability to a piece of text. What does it mean? For example, if we have some text that contains capital T words, then the probability of this text, according to the language model, is this. Because we can calculate this probability using the total probability theorem. I don't exactly remember the theorem's name, but first you can calculate the probability of the first word and calculate the probability of the second word given first word. And for the capital T word, teeth word, you can condition this probability with the previous words. And you can condense this expression using this product operator. And our language model gives the probability of this sentence. And what does it mean if the probability of a piece of text is high? And what does it mean when the probability of a piece of text is low? When the probability is high, that means that sentence is quite natural. And if the probability of the sentence is not high and low, that means it's unnatural. Because the probability itself means that that sentence occurs often. And if the probability is quite low, that means that sentence is unlikely. So for example, if you have some text, the probability of this sentence might be quite moderate. However, if you say, example 4, if text some have the probability of this text might be very low because it's not natural and it's not grammatically correct. So the probability of a sentence or a piece of text means its naturalness. Okay? And we use language models every day, actually. When we type, our keyboard gives some suggestions for the next words. And this is done through language model. And when we search on Google, Google also predicts the next word we want to type. That is also done by language model. And how do we construct language models? This is the question. How do you learn a language model? Before deep learning came out, people used n-gram. And what is n-gram? N-gram is a chunk of n consecutive words. And there are various n-grams. And when n equals 1, that is called unigrams. That is the probability of each word. And bigram is the probability of 2 consecutive words. Trigram, 3, 4gram, 4. And the idea is like this. Collect the statistics about how frequent different n-grams are and use these to predict next word. So in this example, the students opened there, then we can use 1, 2, 3, 4 gram, and 5 gram. And let's see what is the most probable word that will come here. We can calculate the probability using 4 gram and 5 gram. First, okay, let's have a detail. Let's have a look at details. First, we make a Markov assumption. xt plus 1 only depends on the preceding n-1 words. Even though we have more contexts, we just assume it only depends on n-1 words. And how do you calculate this probability? This can be done using the definition of conditional probability. And this becomes, okay, so probability of n-1 gram in so this denominator is the n-1 gram and numerator is n gram. Okay? And how do we calculate these probabilities? We can't. So what we do is we just count them in some large corpus of text and we approximate the probability. That's what we do. Okay, so this is how we calculate the probability of the next word. Let's have a look at one example. Suppose we are learning a 4 gram language model. Then even though we have other contexts, we're going to remove them, discard them. And we condition on these 3 words. Students opened there. Then we can count the number of other words. And let's say students opened there occurred 1,000 times in our corpus. And students opened their books occurred 400 times. And students opened their exams 100 times. Then the probability of books will be 0.4. And the probability of exams, given this context, is 0.1. Then we can expect that the next word that will come here is books. However, when we closely look at the discarded context, it is as the proctor started the clock, the students opened their, in this case, proctor or TA. And when you look at this, you might say, oh, books might not be the correct word. However, exams is the correct word. And here you can think, oh, even though we have 4 contexts or 3 contexts, that might not be enough. And we should not discard the proctor context because it gives a crucial insight to what next word would be. And you can think of it as sparsity problem with n-gram language model. What if, let's first look at the numerator. What if students open their W never occurred in data? Then W has probability 0, even though that might be probable. And partial solution to this sparsity problem for numerator is adding small delta to the count for every word in our vocabulary. This is called smoothing. And the second problem is when the denominator, students open there, never occurred in data. Then we can't calculate probability for any W. And in this case, one partial solution is just condition on opened there rather than considering all these 3 words. This is called back off. And the thing you need to note here is increasing n makes sparsity problems worse. Typically, we can't have n bigger than 5. Okay? Because n-gram does not think about the context or the meaning of the words, but it only thinks about the frequency. That is the problem. The semantics are ignored in this case. And another problem with n-gram language models is storage problems. We need to store count for all n-grams you saw in the corpus. And as we increase the number of words or n-grams or increase in corpus, increases the model size. And to be more accurate, we need to increase the corpus size as well as the number of contexts. However, before deep learning, n-gram was actively used in NLP, natural language processing research. And you can build a simple trigram language model over a 1.7 million word corpus, Reuters, in a few seconds on your laptop. And you can try this following this link. And today, and then you get the probability distribution using trigram. And as you can see here, the sparsity problem occurs. Not much granularity in the probability distribution. Only 2 words get the most of the probability, and the rest get like meaningless probability. Today, condition on this, we get the probability distribution, and according to this probability distribution, we sample the next word. Sampling, for sampling, we have 2 ways. The first one is deterministic. And the second one is stochastic. Deterministic sampling samples the most probable word. Here, just the company. In this case, we are going to make the same sentence all the times. However, if you follow stochastic sampling approach, then we just assign probabilities to these words according to this probability distribution. And following this probability distribution, we just sample one word. So even though company and bank might have higher probability, but still we can sample Italian or price. Anyway, let's just assume that price is sampled. And after that, we condition on the two words and the sample again. And this is what we get following the trigram language model. Today, the price of gold per ton, while production of shoe less and shoe industry, the bank intervened just after it considered and rejected an IMF demand to rebuild depleted European stocks, September 30, and primary 76 CTS a share. Surprisingly, it is so grammatical. However, the content is incoherent. It does not make any sense. You don't know what it's talking about, right? Therefore, we need to consider more than 3 words at a time if we want to model language well. However, as we saw, increasing n worsens sparsity problem and increases model size. And that motivates neural language model. How can you build a neural language model? Recall that the language modeling task is given a sequence of words. We want to output or get the probability distribution of the next word. Then how about a window-based neural model? It is similar to CNN, or we can use fully connected layer. Fixed window neural language model, we can consider only like predefined length of context. So still, we might ignore these contexts. And a fixed window neural model looks like this. First, we get the words, a sequence of words. This is one-hot vectors. And we concatenate word embeddings. We first embed each word using the word vectors we developed in the last session. And after that, we concatenate or do some different operations, manipulate them, and then we pass them through a hidden layer or fully connected layer. Then we get the output distribution using the softmax function. Then we get the probability distribution for all the vocabulary, all the words in our vocabulary. And in the early 2000 and 2010, a neural probabilistic language model was prevailing. The improvements over n-gram language model are as follows. There is no sparsity problem because these words care about the context and the semantics. N-gram models only think about statistics, no semantics. And we don't have to store all observed n-grams, so we don't have storage problem. Still, there are some remaining problems because the window is fixed and the fixed window is quite small. And enlarging window enlarges the parameters, and it's going to be very slow or very hard to train. And the thing is, even though we enlarge the window can never be large enough. Because let's think about like the SAT or Korean SAT section. In this paper, like A4 paper, the half of the page is filled with text, and there are like few questions, like 1, 2, 3. Even though we enlarge the window size, we cannot cover all this text in one window. Or even though we make that big window, what if we want to read a book using our language model? Then it's not going to be feasible. Okay? And another problem here is x1 and x2 are multiplied by completely different weights in W, meaning no symmetry in how the inputs are processed. So, for example, if we sweep, let's say the comes here, like, and the students opened. In this case, this the might be processed in a different way than when it was here. This is not intuitively correct. The same word in totally the same context should be processed in the same way. So these are some problems of window-based neural models. Okay, to summarize what we've discussed up to this point, think about this question, pause the video and think about it on your own, and let's check the answer together. All right, let's check the answer together. The answer is the third option. Language modeling is the task of predicting what word comes next. It is correct. This is literally the definition of language modeling. And n-grams entails a Markov assumption. We cannot consider all the context given because it's too long. And a fixed window neural language model solves sparsity problem. We don't have to think about each frequency of each pairs. And we saw how we can generate new text using language models. Okay, from now on, let's talk about recurrent neural networks. So vanilla neural networks can only take in one input and output just one type of output. However, we want to process sequences, and input can be just fixed. However, output can be a sequence. One example of that task is image captioning. Given an image, we want to generate the description of the image, which is a sequence of words. So here we get just one input and multiple outputs like this. And given a sequence of video frames, video consists of multiple frames, and we want to predict what action is in the video. In that case, we receive multiple inputs and output just one vector. Another case is many-to-many video captioning, like sequence of video frames and captions for each frame. And you can see here that there is some lagging. However, there can be different types of many-to-many, like no lagging, but for each word, there is output, like this. This is video classification on frame level. And another thing is, you can sequentially process non-sequential data. For example, image itself is not sequential at all. However, you can process images. Let's say this is just one image. You start from this position and move to the next position like this, and the next. Sorry for that. So move on, start from here, and then move on to next, like this. So we sequentially process, like the direction might be arbitrary, like this. So you can process non-sequential data in a sequential way. That is also possible. And by doing so, you can generate images using rnns. Okay. Then what is neural network? Recurrent neural network. The key idea is like this. RNNs have an internal state that is updated as a sequence is processed. Another view is like this. We are going to apply the same weight repeatedly. And we don't have to, let's say, even though the sequence length is 100, we don't need 100 weights. However, we are going to just use one weight to process all these sentence inputs, sequences. Therefore, we are reusing this W over and over to process the input sequence. However, we also keep track of the hidden state. This hidden state is updated using this same weight, and it becomes H2, X1 and H1 becomes H2, and W receiving X2 and H2 generates H3. Okay, so the weight here, this is fixed. However, H varies over time as the input sequence varies, and X and H can generate new output. And when we unroll this RNN into time sequence, it looks like this. This is called unrolling. Even though, so this is when time is 1, time sequence, time step is 2, time step is 3, time step is t. So it is just one RNN, single RNN. However, its state is changing over time. And how does it actually change? We can process a sequence of vectors x by applying a recurrence formula at every time step. How do you calculate the new state? There is some function with parameters w, and this function receives old state and input vector at some time step t. And combining these two inputs, it generates new hidden state. And using this new hidden state, you can generate output at time step t. So using the new hidden state, we are going to use another function with parameters w sub o to generate output. So actually we have two w's, h, h, w, x, h. So we calculate the multiplication of these two matrices and pass through some functions and then generate new state. And this new state changes h to y. Okay. So we initialize h in some way, and this becomes h1 when there is an input at time step 1. Okay, that happens again and again. And you notice we apply the same function and the same set of parameters at every time step. So we don't have to equip ourselves with multiple parameters to deal with multiple time step data. And this is vanilla recurrent neural network. And sometimes it's called vanilla or an Elman RNN after Professor Jeffrey Elman. And this function actually looks like this. This HH and XH times xt times ht minus 1 gets added, and we pass through hypertangent. Then we get new hidden state. And to update or generate the output, we apply another weight, hy. And we also need to think about the computation graph to think about the backpropagation. x1, x2, x3, xt, and we reuse the same weight matrix at every time step. And in the case of many-to-many, we calculate many outputs like this, and we calculate losses. And here, you need to notice the gradient occurring here flows all the way back to h0. And this gradient flows all the way back to h0. So this component, h2, receives gradient from L2, L3, LT. And the component at time step t receives gradients from loss t, capital T. Okay? So you need to accumulate gradients to calculate the gradient for the weight W. And we're going to have a close look at how we can implement this in the implementation session. And we calculate the global loss by summing up all the sub losses. And in the case of many-to-one case, many-to-one, we have just one loss. And this loss flows all the way back to H10. Okay? And there are, of course, the case where one-to-many. And in this case, what do we need to inject in our recurrent neural network? There are two options. The first option is just inputting zeros at every time step. Another option is we input the previous output. So this one becomes the next input, and this one becomes the next input. There are two options. And you can combine the RNN architectures. We saw one-to-many, one-to-one, many-to-one, many-to-many. And you can combine many-to-one and one-to-many in this way. So many-to-one encode input sequence in a single vector. And using this encoded vector, you can produce output sequence. And when do we need this kind of architecture? That is for translation. Let's say we want to translate Korean into German. However, because of the grammar difference, in the case of Korean, the subject and other components, and then verb, let's say this happens. However, in the case of German, let's say English. Subject, verb, and other components, like this. And because the grammatical order of words are different, you can choose many-to-many RNN structure or architecture. However, you need to encode all the information of this sentence into a vector, and using this vector, you need to generate the English sentence. So this is one example of where many-to-one and one-to-many can be applied. And another example using RNN is character-level language model. An example sentence is hello, and the vocabulary is HELO. And as we saw, this one-hot vector becomes word vectors. And then after hidden layer, it generates outputs. And we want that the probability distribution is the maximum for the target character. Okay, like this. In this case, the probability distribution is quite different from what we expected. Then here, a large loss will be occurred. And at test time, what we do is we input one word, one character, and we sample from this softmax. And then this output becomes the next input. Okay, we follow this procedure like this. So at test time, sample characters one at a time and feedback that sample to the model. That is how we generate a text. And we saw this when we want to embed our words, one-hot vectors, into word vectors. We don't actually need to perform matrix multiplication. What we want is just one column. Therefore, we're going to just get one column rather than doing matrix multiplication. And that is done through embedding layer. Okay, training on RNN language model. From this corpus, you predict the probability distribution. And if this is quite different from what we expected, then a large loss will incur. And then we calculate negative log probability for opened because the next word is opened. There, exams, and we sum up these losses. And at the training time, we inject the ground truth words like this, rather than sampling from here and then injecting, inputting this output. We just input the ground truth inputs. This is called teacher forcing. Because at the beginning of training, the sampled words might not make sense and it takes longer time to train. That is why we are just inputting the ground truth labels. Okay, and computing loss and gradients across the entire corpus at once is too expensive in respect of memory. In practice, consider just a sentence or a document rather than the whole corpus. And recall stochastic gradient descent allows us to compute loss and gradients for all small chunk of data and update. And we compute loss for a sentence, actually a batch of sentences, compute gradients and update weights. Repeat on a new batch of sentences. And backpropagation through time, we forward through entire sequence to compute loss, then backward through entire sequence to compute gradients. However, that is computationally very expensive. So what we do is truncate the backpropagation through time. Roll forward all the way through the ending point to the end point and backward through chunks of the sequence instead of whole sequence. And in the next chunk, we do the same. Rather than going through back to all the way to the front, we just cut the gradient at this step. And T might be 10 to 12, 20. So we carry hidden states forward in time forever, but only backpropagate for some smaller number of steps, like 10 or 20. Like this, we repeat this process. So what's the derivative of J with respect to the repeated weight matrix WH? The answer is like this. We need to sum up all the gradients. So I told you H, for example, 4 depends on loss 4, loss 5, loss T. However, the gradient with respect to a repeated weight is the sum of the gradients with respect to each time it appears. So there is many paths that H4 is affecting, and we need to gather all these back-propagating gradients, upstream gradients. And we saw this a lot, multivariable chain rule. If this one output, T, contributes to xt and yt, then we need to gather gradients from these two paths. Okay, gradients sum at outward branches. If there are like 3 branches, we need to collect gradients from 3 paths. And you can have a look at this on your own, backpropagation through time. This is quite simple, okay? And in practice, often truncation means after 20 time steps, okay? And we are going to implement this backpropagation through time in the implementation session, so don't worry too much if you don't understand what it means. And using Python, you can just use 112 lines to learn character level language model. This is quite easy. And you can train your RNN using Shakespeare's text, and it can generate quite plausible text. At the beginning, it does not make sense at all, but as time goes on and on, it seems like that of Shakespeare, okay? And you can even make a sentence like this. It knows where to change a line like this, where to make a blank line. And you can also train RNN using LaTeX source code, and it generates LaTeX like this. It's quite okay. It looks plausible like this. And you can even train code like bear code, C code, or C++ code. And it can generate C code. Nowadays, Copilot is helping you coding quite a lot, or ChatGPT. Okay. This, like this. And OpenAI is using these language models very well. Then how do we evaluate our language models? The standard evaluation metric for language models is perplexity. What does it mean? Perplexity is the inverse probability of corpus according to the language model, and normalized by number of words. And when you closely look at this, let's say, given some context, our language model, let's say the student opened there, and our language model predicts the probability distribution is like this. Let's say exams have the probability of 1, and other words 0, like this. Then the perplexity is 1. However, if our language model predicts the probability distribution of the next word is exams is 0.2, and paper 0.2, and laptop 0.2, then this perplexity is going to be 5, because it's the inverse of 0.2. And you can see perplexity as how many options our language model have for the next word. And if we have less options, that means our language model is quite confident. In this case, it is confident that the next word should be definitely exams rather than laptops or books or other words. So lower perplexity is better, because our language model is certain that the next word should be between these, let's say the perplexity is 2, that it means these two have the highest probability, and it is not perplexed. Okay. And rnns greatly improved perplexity over what came before, like n-grams. However, still it has quite high perplexity. Okay, the trade-offs are like this. rnns can process any length input, and computation for step t can use information from many steps back. And model size doesn't increase for longer inputs. It actually stays the same. And same weights applied on every time step, so there is symmetry in how inputs are processed. However, recurrent computation is slow because to calculate, let's say y, okay. To calculate y at time step t, we need hidden states from t-1, t-2, and h1. And we cannot suddenly calculate yt. However, we need to do this like step by step, and this process cannot be parallelized. Therefore, the recurrent computation is slow. And another thing is, in practice, it is difficult to access information from many steps back, although it is an advantage of RNN, but in practice, it is not the case. RNNs are known to be capable of processing 100 time steps. Okay, that was RNNs. And let's implement RNNs. Recurrent neural networks. Similar to normal computation modules, we need to define the initializer and the forward. And backward. Okay, let's start implementing the initializer. We need to have wx and whb. And we're going to store the parameters like this, and grades and be zeros like wx, and be zeros like wh, and be zeros like b. And we need to keep track of some values, and we're going to store that in our cache. And how do we calculate the forward? We first retrieve our parameters, and we first calculate the new hidden state. This is the computation we saw in the slides. And we calculate the next hidden state using hypertangent like this. And in our cache, we're going to store x and h previous and h next. Okay, this is quite easy. And for the backward, this is our first PPP exercise. Think about this on your own and see you in the next video.